As we start out here in lesson for section 5.4, if you haven't done so already, there's a lot of notes in this section. In fact, primarily this section is all about notes. We're going to have a few examples, but it's mainly the notes. So if you haven't read these, would you mind pausing the video and just reading the notes at least a couple times? Because I'm going to go through and make some highlights. And as I talk about the highlights, it'd be great if you kind of knew exactly what I was talking about. In this first portion of the notes, it's basically just doing a recap on what the mean value theorem for derivatives was, because what we do is we have a mean value theorem for integrals and we do have one for derivatives. So going back and recapping the derivative one, it was basically saying that if you have a continuous curve and you have points A and B, the slope of the chord that connects points A and B is going to equal the slope, the instantaneous slope of some point C on that curve. So the slope of the line here is going to equal the slope of the line here. It's just here I'm connecting points A and B on the curve, but this is going to be exactly one point in the curve. Okay. Now if we look at, and obviously real quick, the derivative is all about the slope, remember? And so that's why that mean value theorem for the derivatives was focusing on slopes between points. Okay. When we go over here to theorem 3 for this section, we have a mean value theorem for integrals. Remember, it says definite integral, so that means we're not just taking a general integral, we're actually going to go from point A to point B, okay? And remember, integrals are all about areas under a curve. And so what the mean value theorem for integrals is basically saying is that if you, and the easiest way I can look at it is how I kind of wrote it out. If for some specific value C in this closed interval A to B, the area under the curve, so all of this area from A all the way up to B, all of this area under the curve right here can be estimated by a rectangle, where specifically when we choose the correct C, then saying the area of this whole rectangle that's sitting under here as well, so just of this rectangle that has a little bit that goes out and a little bit that stays under, the area of this rectangle equals the area of that blue shaded region I just drew. Okay? And that's for a very specific value C, just like for a very specific value in C up in the mean value theorem for derivatives, that we'll get those two slopes to be equal. For a very specific value C in here, we'll get the area to equal the average value there. And if you look kind of up in the formula, remember that was this last part right here was the formula that we used at the very end of the last section in 5.3 on how to find the average value of the function from A to B. So what this is saying is the whole average value of the function from A to B can be equaled to just plugging C into your main function, and it'll give you there. So there's some very specific point in C, very special point in C, that when I plug that point C in there, it equals the average value of the whole entire function from A to B. Very, very special and important tool. Okay, so we go to theorem 4, the fundamental theorem of calculus. Sounds important, doesn't it? The fundamental theorem. And what this theorem is saying is basically if you have a function that's continuous, then its antiderivative is also continuous, and you can take the derivative of it and get back to the original function. So if I have an antiderivative f of x and I take the derivative of it, so this is just, remember this part right here is the antiderivative, and this is showing me I'm taking the derivative of it. Specifically, I really want to point out these endpoints. If you're going to go from some number up to the variable x, okay? Because look, we're taking the derivative with respect to x, the derivative with respect to x. It's always going to be from some number and your upper bound is going to be x. Then really what comes out is a function of x. It's very important. That's the key I want you to know with this part 1 of the fundamental theorem, is that as you take the derivative of the antiderivative, or the derivative of capital F of x, from a to the variable x, what you're going to be creating is going back to the original function, but in terms of x. Okay? So if this upper bound is something other than x, like x squared, you have a whole other set of rules you can do. Okay? Let's go on to part 2 of the fundamental theorem. This is the one that we are going to use a lot. I put it in a box because in general, if you're finding a definite integral going from a to b, so a number down here and a number down here of your original function, all you have to do is find what this is saying is find the antiderivative, okay? And then this symbol right here is just basically saying evaluating. When you have a vertical bar like that, we're saying we're going to evaluate. So we're going to evaluate the antiderivative from A to B. And that's as simple as saying plug in the top number into your antiderivative, always minus the bottom number plugged into your antiderivative. Okay? So the integral, the definite integral from A to B, is you find your antiderivative, then plug in the upper bound, plug in the lower bound, and then subtract the two together. It's going to be used a lot. And specifically in a ton of problems, anytime it asks you to find the area between the curve and the x-axis, this is what we're going to be doing. This is the formula we're going to be using. Because it's going to say find the area from like 0 to pi of this graph between the curve and the x-axis, and this is what we're going to do. We're going to find the antiderivative, plug in the top bound, plug in the lower bound, and then take the difference between the two. Okay, and going through here are just some basic notes. I'll let you guys take some time just to read through those. It's just saying basically the connection between antiderivatives and derivatives is just they just reverse each other in operation. Okay. And with this net change theorem, if we kind of just go to the definition itself, which is this line right in here, what it's saying is, okay, remember this is finding the area under a curve. Okay, if I just had f of x as is, the antiderivative finding the area of a curve, but by taking the derivative, remember the derivative finds your slope, it's your rate of change. Okay, so the rate of change as x goes from a to b is obviously all you're doing is plugging in the upper bound minus the lower bound. Okay, so it's very similar to what we just saw just a second ago. And in terms of word problems, this happens a lot, especially for all of you guys that are engineers. If you have a main function and it's s of t, that's always like a position value. Okay, as soon as you take the first derivative, you get velocity. If you took a second derivative, you get acceleration. So the function as is will tell you, the main function will tell you how far you've gone from t1 to t2. So it's just the displacement. Okay, I've gone, from 10 feet to 20 feet or something like that. That's what your first function is going to tell you over a time interval. Now, as soon as you take the derivative, then you're going to be finding like the speed, the velocity in a specific direction. And then the second derivative will tell you all about acceleration. So this whole concept right here of velocity, where velocity is the first derivative of your displacement function, and then acceleration would be your second derivative, it's huge when it comes to the world of engineering. Okay, well, let's keep moving on just for a second. And in summary, this is some great points. Okay, to find the area between the graph and the x-axis, that's the key. The area of the graph, and it has to be the x-axis. Okay, over the interval from a to b, we're going to divide the area region into if you have like a portion above the x-axis and a portion below the x-axis, we need to find exactly where those x-intercepts are. So that's the first step. Then we're going to integrate the function, and then we're going to take the absolute value of the results to find the total overall area. Okay, so starting out, we have an example. We want to find the area, the integral, from -2 to 2 of x cubed minus 2x squared plus 3. Okay. So the first thing I want to do is find the antiderivative, and using all of our rules. So the antiderivative of x cubed would be x to the 4th over 4, and then we're going to evaluate that from -2 to 2. Minus 2, and then the antiderivative, or the integral of 2x, or just x by itself, would be x squared over 2. And again, we're going to evaluate that from -2 to 2. And then the integral, or the antiderivative of any constant, remember we just go 3x. Just add the variable to it, and -2 to 2. Okay. So if I pull off just that coefficient on that one, I'm going to write it as 1/4. And it's always the upper bound plugged in, so 2 to the 4th, minus the lower bound plugged in. Okay, so that's how we're going to evaluate that first term. Okay, minus the 2's are going to cancel. So now I'm going to evaluate, I'm going to go ahead and just put this in parentheses so we can show first term, second term. Okay, so minus the upper bound, 2 squared, and then minus the lower bound plugged in, -2 squared. Okay, then plus 3. The upper bound plugged in minus the lower bound plugged in. Okay, so to finish this up, let's go to inside each parentheses. This is basically saying 2 to the 4th, so 2, 4, 8, 16 minus 16, so that's going to go to 0, which is going to take that term away right there. 2 squared is 4, minus 4 again, so that takes that term away. So all we have left here is just, let's see, 2 plus 2, which is 4, and 4 times 3. We'll get us an answer of 12. So all in all, what we just basically found is if I graph that curve, x cubed minus 2x plus 3, and I graphed it and I looked specifically at the area between -2 and 2, I just found the area of that whole curve to be equal to 12. Okay, so here in example B, we're just going to take the integral of 1 plus cosine x dx. And so just going term by term like we did before. The integral of 1, looks like our variable is x this time, so the integral of 1 will be just x, evaluating from 0 to pi, and then plus the integral of cosine x. Well, the integral of cosine x would be 1 over any number attached there, which is just 1. So it looks like it's going to be a sine of x, evaluated from 0 to pi. So in each case, we're going to plug in the upper bound to the variable. So I'm going to plug in pi into the x, minus the lower bound plugged in, and then plus sine of the upper bound plugged in, minus sine of the lower bound plugged in. Well, sine of pi is 0. Sine of 0 is 0. So it looks like your answer here for the area under the curve between 0 and pi is just going to be pi. Okay, example C. My function this time is secant u tangent u du. And with a 4 in front, so I can almost write that as I want to pull the 4 out and take the integral from 1 to pi over 3 of secant u tangent u du. And looking at this kind of a little more closely, just, it always goes from a lower limit to an upper limit. Pi over 3, isn't that larger than 1? You just have to kind of check for a second. You're like, ooh, that's in a fraction. It's got to be small. But no, it's actually larger. But all right, let's look at we have a formula for the integral of secant u tangent u. All that's going to equal is just secant of u, because our variable this time is u. So it's going to be 4 times secant of u, evaluated from 1 to pi over 3. So I'm going to pull the 4 off the front. I'm going to plug in my upper bound, so secant of pi over 3 minus my lower bound plugged in, so secant of 1. Further evaluating, then we'll get 4, and then secant of pi over 3. Secant is just the reciprocal of your x value, so at pi over 3 our x value is 1/2, so the reciprocal of 1/2 is 2. Okay. And then we want the reciprocal of the x value at 1. And you know what? I was looking at that, I was like, that looks really weird. Secant of 1, that's a little bit different. I just paused the video real quick, because I've been pulling these from the book. That actually is a 0. It came across looking like a 1. That should be a 0 right there. It's going to make a big difference, because we can actually take a secant of 0. So y'all just place zeros in there. So what is the reciprocal of the x value at 0? Well, the x value at 0 is obviously 1. When you're at 0 or 2 pi, you're at 1. And the reciprocal of 1 is still just 1. So all in all, 2 minus 1 is 1 times 4 is 4. So the area under the curve is 4. Sorry about that, but if it looks kind of weird, like that doesn't seem there, you might just even double check, especially when y'all are writing it down in your notes to work on some problems. That'd be a good thing to look at.